Good afternoon, everybody. I hope you're all healthy and safe at home. So, we are moving on to section 1.3 of the first module. In this section, we are going to discuss the topological and geometrical notations. So, first, we'll recall few definitions. The first definition is that of an open ball. An open ball of radius r greater than 0 centered at x dot is defined to be the set, which is denoted by dr of x equal to the set of all x such that norm x minus x dot is less than r. So open ball is the set of all elements whose distance from x and x dot is less than r. So the radius of that open ball is r and the center is x dot. Next is the definition of open set. A set O contained in X is said to be open if for every X belongs to 0, there exists an R greater than 0 such that dr of X, that is the open ball containing X, is contained in the set O. So a set is open if for any point in O we can find an open ball contained in the set O. Next is the definition of closed set. What is a closed set? A set F subset of X is said to be closed if for every sequence Xn belongs to F that converges to some X belongs to capital X, it follows that X is an element of F. So here capital X is the norm space. So when can we say that a set is closed? A set is said to be closed if for every sequence contained in set, the limit point is also contained in that particular set. So that's it for the closed set. Now next we'll define what is meant by closure. The closure A dash, it is denoted by A dash, of a set A is a set of all x belongs to capital X such that there exists a sequence xn belongs to A with xn converging to X. So what is it? It is the closure is the collection of all limit points of that particular set. Next is the definition of dense set. A set A subset of X is said to be dense if and only if A closure equal to X. So I'm sure you're familiar with all these definitions which you have studied in topology. So we had defined what is an open ball, an open set, a closed set, what is a closure, and what is meant by a dense set. Now, what I want you guys to check is you have to check whether the norm function is continuous or not. In the last section, we had defined what is a norm. Norm is basically a function from the space to R. So I want you guys to check whether that function is continuous or not. You can refer the textbook for a hint which is given. So next we'll move on to lemma 1.3.1. The lemma is pretty much simple. It states that if O is an open set, then F is equal to O closure will be a closed set. And conversely, if F is a closed set, then O equal to F closure is an open set. So what we have to prove is we have to show that if O is open, then its closure is closed, and if F is closed, and its complement is open. So how can we prove this? Suppose that O is open. Suppose that O is an open set. Now we need to show F is closed. So by definition of closeness, what is it? If there is a sequence xn, say xn belongs to F and xn converges to X, to show that F is closed, we must show that X belongs to F. Okay, so suppose, if possible, suppose that X does not belong to F, that is X belongs to O. Now, as O is an open set, we can find an R greater than 0 such that dr of X, that open ball containing X, will be contained in O. This is by definition of open sets. So, now as we have assumed that xn converges to x. We can find an n. We can find a large n such that distance of xn and x will be less than r. Okay, now if this is true, that is if the distance of xn and x is less than r, then by the definition of open set, what we can conclude? We can conclude that xn will be an element of O, right? So this is a contradiction to the fact that xn belongs to f. So our assumption was wrong. So x has to be an element of f. So the proof is simple. We just have to show that f is closed. For to show that f is closed, we had to show that for any sequence xn in f such that it converges to x, x must also be an element of f. So we have shown that. Now conversely, we must show that if f is closed, what should we show? We should show that O equal to f closure is open. This is what we must show. Now, to show that a set is open, what must be shown? You must show that for every x belongs to O, we can find an R such that dr of x is contained in O. This is what we have to show. So suppose that there exists an x belongs to O such that the open ball is not contained in O. Okay, that is, it is not wholly, this open ball containing x with radius r is not wholly contained in O. Then what can we do? Then we can always find an epsilon n. Now as it is not fully contained, we can find an epsilon n greater than 0 such that there exists an xn belongs to f. So as the open ball is not contained in O, some portion of it will be in O complement, that is f. So we can find an xn belongs to f such that distance of xn and x will be less than epsilon. So this implies xn converges to x, and as f was closed, we can say that x will be an element of f, which is a contradiction because we had assumed that x is an element of O. So our assumption was wrong, that is whenever we have an x belongs to O, dr of x will also be contained in O if f is equal to O complement is a closed set. So that's it for the proof of lemma 1.3.1. So let me state the lemma once again. What is it? It states that if O is an open set, then f is equal to O closure is a closed set, and conversely if f is a closed set, then O equal to f closure is an open set. So let us discuss a few more definitions. First is the definition of the interval. For any 2 points x and y, the set lambda x plus 1 minus lambda y for 0 less than equal to lambda less than equal to 1 is called the interval, and it is written as I of x comma y. Next is the definition of a convex set. A subset M of a linear space E is said to be convex if and only if for every 2 points x and y in M, the interval I of xy is contained in M. Next is the definition of bounded set. A subset M of a normed space X is said to be bounded if there exists a number C greater than 0 such that for all x in M, we have norm x is less than C. So when do we call a set to be bounded? We call a set is bounded if all its elements are bounded by a particular value C. Next, I want you guys to verify that the intersection of a convex sets is again convex, and it is simple to prove that. You can try it. And the next thing is to verify that the unit ball of a space is convex and centrally symmetric. So the definition of the unit ball and central symmetric, you can refer to your textbook. So that's it for today's class. Thank you. Stay home and stay safe.